couple weeks ago, we made a video how to find TraceLine in Assault Cube and how to call it using inline assembly. This video is going to be the same thing, but in CSGO. So TraceLine is a function that takes two positions in 3D space, draws a line between them, and walks across that line and tries to detect a collision. So TraceLine is detecting the line between me and him, and once we hit, TraceLine detects the collision, and it'll return usually the entity that it collides with. So we are going to find that in CSGO. In the previous video, you will have learned that every game has, I don't know, 5 to 15 different functions that all do this TraceLine ray trace functionality. It is the same thing with CSGO. So let's get right into it. First thing we're going to do is we're going to run our offset dumper. Once we've got that, we can load it up into Cheat Engine. That all adds all these symbols to our cheat table. We're actually going to delete those, but we are going to be using them. First thing we're going to do is we're going to pimp out our cheat table. So let's add some addresses. We'll select pointer. We're going to paste in client panorama.dll, and we're going to add DW local player. That's going to give us the address of our player object. We're just going to call this local player pointer. Next, we're going to do the same thing as a pointer, and we're going to add DW local player. But in our offset, we are going to add m_vec origin, and that's offset 138 in this case. And we're going to change this to a float. So this is our vec origin. We're going to do the same thing. Pointer, add it in, m_vec origin, and we're going to do +4, and this is going to be our vec origin y. Another one, vec origin +8, and that's going to be vec origin z. Let's add one more, and it's going to be m_vec view offset +8. So that's going to get our vec view offset and our z coordinate for that. And what that is the difference between our vec origin z and our view, our I position. Let's save that. In the Assault Cube video, we did find out what accesses on our ammo and on our local player position, and that led us back to TraceLine. In CSGO, it is not actually going to work that way because this game has many different TraceLine functions, but the one that's easiest to use is not actually used by your game on a regular basis because they have TraceLine wrappers, which are specifically used just to detect entities, but we're going to do something a little bit simpler. So there are two ways to easily find these functions. So let's go into IDA. First thing you're going to want to do is go to segments, rebase the program, rebase the whole thing to 0x0, and that way every address will be a relative offset. This way you won't have to resolve any sort of relative addressing. Whatever this number is here, it's a relative offset from the base address of the module. Just like in Cheat Engine, that's how we're going to see it as a module base. Once the rebasing is done, I'm going to show you two ways to find it. One by using strings, and the second way with using the runtime type information, which we're going to expose by using class informer. Now you'll notice I am looking at engine.dll, not client panorama, because this is an engine function. Think about what a game engine does. The main purpose of a game engine is to do all the 3D game programming. And TraceLine or ray trace is something that would fall into that category. So we are going to look in engine.dll. Let's look at the strings, and let's just look for the word trace, or TraceLine, or TraceRay. In this case, in CSGO, it is called TraceRay. So there we have it. So let's open that, and we hear this is the string in memory, TraceRay, and we want to find cross-references to it. This is functions that access that string. And we find one here, and as always, I'm just going to F5 it and take a look at what we have. We have this weird, I don't know what this is exactly. Maybe it has something to do with CVARs. I don't know what the CV means. But if we just look at this, it's doing some stuff with floats. It's referencing the string TraceRay. Pretty sure this is already it, or it's going to be close to what we're looking for. If we scroll up, we can see it's a this call, so it's a member function. And it has 1, 2, 3, 4, 5 arguments. One of them is the this pointer. And so let's just call this TraceLine. What I like to do is write this right here, and then leave these numbers here so that you never forget what that address is. Now let's use Class Informer. So we go to Plugins, Class Informer. Once that's completed, we have all the different vtable class names here. So let's do Control F and look for trace again. And we're going to find several things. We have trace list data, trace filters, CEngineTrace, and CEngineTrace client. These are the two that are most important to us. And let's just open CEngineTrace and take a look. We can see that the fifth index in the vtable is our TraceRay function. We're looking at CEngineTrace. If we scroll down, maybe scrolling up, we have CEngineTrace client. Also, the same index is the same function, and then CEngineTrace server is the same function. So client or server, they both have access to this function. And this inherits from CEngineTrace, which is the class for the interface EngineTrace. So now let's get an idea about what we're looking at. Let's go over to the source SDK on GitHub and just search for the word EngineTrace. Here it is, abstract class. This is just a define or a type def for an interface. That's all it is. What is an interface? Well, you see all of these are set to 0 because an interface doesn't define the member variables. All it does is define what member functions that derived classes need to define. So an abstract class or an interface isn't actually used as a class itself. Classes are derived from it. In that class, you can add member variables, and then you have to define all these things. We can see here is the TraceRay function, and if we look at indexes, we have 0, 1, 2, 3, 4. If we go back to here, 0, 1, 2, 3, 4. So that is the correct one, as long as the game hasn't updated. Again, this is the core part of the engine. These things don't get updated. And the label says a version that simply accepts array and can work as a trace line or a trace hull. First argument is array, a mask, a trace filter, and then a ptrace. It has no return value, but it does access ray by reference, trace filter, and trace by pointer. So ptrace is going to be what contains the information about what sort of collisions occurred. We can look at the other clip functions, clip ray to entity, so this can trace against a particular entity like a player object. So we could certainly use one of these. These functions are probably functions that the game itself calls. You'll see that this isn't used in the context of finding if a bullet hits someone, but we can still use it in our cheats. So I wanted to show you the SDK so you know what we're looking at. Now let's look at it in Sheet Engine and IDA and try to get a more reverse engineering approach to it. So if we go here, we can get the address of it. It's offset 1FAA90. Let's grab that. Let's go to Cheat Engine Memory View, and let's do Control G, to jump to the address, and we're going to do engine.dll plus this. Now we can see the TraceRay string is right here, so this is exactly what we're looking at. This is the benefit of rebasing the modules in IDA Pro, is you can just access this stuff really easy. So let's set a breakpoint and see what this thing does. So the first thing when we're talking about TraceLine is I want to see it calling TraceLine from me to the enemy or something like that. So what I'm going to be looking for is my entity object. And actually, I've actually done this wrong. We don't want this as a pointer, so grab that and just add this in right here. And now what we get right here is this is the address of our entity object. So now we're going to go back here and we're going to see, are we going to find that address in one of these registers, or are we going to find it on the stack? So to see the full stack, you need to right click here and click full stack. Now we will see all the local variables and arguments right here. So again, what I'm going to do is we're looking for this address here. I don't see it in any of these. Nope. I do not see it as a variable that's on the stack here. But what about in the registers? Nope, I don't see it. But let's just run it a few times, and we're going to check both of these things. And if you look at EDI, we see that our address is in EDI. So does this mean that our player object is calling this? No, it doesn't mean that. It means that before this function was called, our player object was put into EDI. The only thing that indicates is that our player object was recently accessed in EDI, which is a pretty good indicator that these two things are associated. You can also see on the stack ESP plus 14, ESP plus 18, the addresses in both of those. So either the function that called this function or another function higher up the call stack was using our player object. So we know this is a this call function, and so ECX contains the this pointer. So let's grab ECX and let's open up reclass. We're opening up reclass because it's just really easy to see RTI, RTTI in a running process with it. And let's just drop this address in. And we can see the runtime type information, see EngineTrace client, see EngineTrace. So we are definitely looking at the right thing and we're in the right spot. So next question is, let's take a look at these stack variables and see how these arguments are getting passed in. If you've done our previous reverse engineering guides on the forum, you know that this call member function, the this pointer is passed into ECX, and then the arguments are passed in from right to left. So this function has just been called, and so the last thing pushed on the stack should be the address of the array. So let's take a look at that. So the last address here is 5B1B65E7. So let's go back to reclass again and drop that in 5B1B65E7 and nothing. I was hoping to either see 3 float values here to represent a array source or destination, or some RTTI saying this is array, but no such thing. What about the next stack variable? We have 3 floats, a something, and then 3 more floats. Let's compare that against what we have here. So we have 798,805, 798,805, and then we have 180. So why doesn't this number match our z coordinate? Well, if you take the vec view offset for the z and add it to our origin z, you would get 180. So that's where that number comes from. So this makes me think this is array, and the array, this is the source operand for the array, and maybe this is the destination. So we're tracing from us to here, but we really don't know that. We're just kind of winging it right now. Let's take another look at some other variables. 46004003. So we have 46004003. We have 0000, not sure what that is. Let's look at the next one, 46DB30. That looks like a stack. Yeah, this is on the stack. So it's just a stack variable pointer. And if we go here, we can see that this object is a CTrace filter simple, which inherits from CTrace filter. If we go back to our SDK here, we can see that the iTrace filter. All right, the next stack variable is 46DB F8. And we have an unknown. I don't know what it is. Let's take a look at the next one. 553E5950. If we open this guy up, this is our local player. We already knew that. So let's go back to this variable here, 46DB40 right here. And when we look at this, we have our local position I coordinates, and then something that's either angles or coordinates. And when I think of array, I think of basically a line between two places in 3D space. So that's 2 vec3s. Kind of looks like what we're looking at. But array can also be used. You can have a source location and then an angle, and that array extends infinitely in the direction of that angle. So maybe that's what we're looking at as well. Let's take a look at this function as it's being called in other cases. So let's do right-click this and change the breakpoint and add a condition. And so we only want to break when EDI equals this. And for some reason, you have to put 0x here. So now when we run, it wasn't breaking actually, because when you do the break condition, it has to be in all caps. So EDI in all caps. Now, every time we run it, EDI is always our local player object. So by setting up this conditional breakpoint, we're getting it to break only when our player object is interacting with this TraceLine function. So we can get a better indicator using information that we do know to understand the information that we don't know. Now what you notice is that ECX is always the same address. So that CEngineTrace class object, it's always the same. If we remove this breakpoint condition, right, and then just do a regular, ECX never changes. Now ECX did just change. So every once in a while, it's from a different address, but it's almost always the same address. So let's go into IDA and try to define this function, okay? So we know that this is the this pointer in ECX. Then we know one of these is like array, and one of this is the collision detection like return. That's usually called trace_t. So we want to locate where those are. We want to find something that's getting accessed by a pointer and it's being changed inside the function. What that means is that that variable is either passed by a pointer or passed by reference because it's not acting on the local variable, it's acting on the pointer. So we can see right here, A5 plus 11, 14, 15, 16. This is very weird numbers to be setting, and it's 1, 2, 3, 4 in a row. It's just very weird to me. But anyways, A5 is dereferenced after adding an offset is added, right? So A5, I think, is the trace underscore T. We can see it's calling memset on trace T and size 0x54, so we know that's the size of the trace T variable, so that will aid in reverse engineering it. If we scroll down, you would think that the information in trace T would be set at the end of the function, and that is what we see here. Before the function ends, it sets 1, 2, 3, 4, 5, 6 different variables in trace T. Could that be two vec3s regarding the position of what it collided into? Very likely. Right here we see a function being called via a function pointer, and it's v29 plus offset 16. So it's basically indexing into the v table to get to this element, and then it's calling this function. So what's v29? V29 is this pointer. So all that's doing, anytime we see the V29 here, we can even rename this to this too. Anytime that this pointer is getting a copy's being made, we're just going to call it this too. This 3. And then we can see when other member functions are being called. And what the hell is the O word? Why does this say O word? This is so bizarre. I've never seen O word before. I've seen D word and Q word, but never have I ever seen O word. I have no idea what that means. Anyways, let's what else can we find? So we see v32 is the address of the C trace filter hit all v table. What's v32? It's weird. So the address of v32 equals v6. So that's just kind of like a copy or a pointer to v32. V32 is a pointer to the C trace filter v table, and that's inside this if statement. So if A4, then V6 uh, becomes a pointer to A4. So this is like a default. So V6 is going to be our trace filter, and if A4 is not 0, then the trace filter is going to have this V table, okay? That's kind of what it looks like to me. So A4 has got to be our trace filter, right? Yeah, definitely. Trace filter. We're going to call this V32 trace filter pointer. V6 is trace filter copy pointer 2, trace filter pointer 2, something like that. Here we have another function call, except it's a member variable of the trace filter class. And if the result equals 2, then we do this. We see some math here with A2. I'm trying to figure out why these variables are so like you would normally see plus 4 plus 8 plus C, you know? But in this case, we just see plus 1, 2, 3, 4, 5. You see plus 1, plus 2, plus 3, but it's each one of these things it's assigning is a float. And that is because this is pointer arithmetic. That's what I thought it was, and then I second guessed myself and I said, no, you're an idiot, Rake. But no, it is true. I made this little project just to make sure. So cat is 4, dog is just a pointer to a float. That doesn't really matter. All that matters is, look down here, cat is 4, cat plus 1 is 5, but when you cast cat to any sort of pointer and you add 1 to it, that 1 turns into a 4 because that's the size of the pointer type, because it is pointer arithmetic. I've never actually seen this while reversing something for some reason, but here it is. So yeah, these are 5 different float variables that are getting assigned different things. So right here, what you see is we have x, y, z, x, y, z. So we know it's 2 floats. I'm really not sure what it's doing, because all it's doing is adding. It's not doing anything else. Anyways, let's keep looking. Another function call from the vtable for EngineTrace. Function call that's not a member function, and it passes an argument 3 and trace t. What is argument 3? Good question. Argument 3, we have trace t, we have trace filter, and then a3. Let's see how a3 gets used. It gets passed in this function here. Not used. It's used here, here, nowhere else. So I'm not sure what that is. But we can look at cheat engine and we can figure that out. So we had trace T, trace filter, and then A3. The passed in reverse order. So the first variable on the stack should be A2. The second should be A3. If we look at cheat engine, for some reason this isn't the first variable, but E690, this one, that's what we think is our array, right? So that's our first argument after this pointer. I think that's our array. So this is, let's just call this array underscore T. Then A3 has to be our mask at this point, right? Mask. So it's tough. How do you reverse the mask? I'm not really sure. Okay, we can figure out that this is a mask, right? So we have right now our array, and then the next variable should be our mask because it was passed in, it was pushed onto the stack before the array address was. So let's look at this next variable is 403b. Well, that's just like basically an integer, and that's all the mask is. The mask is just a bit field, right? It's a bit mask. So it makes sense that this isn't a pointer, and it's not anything that makes any sense to us, right? If we go to that, it's not an address. So yeah, that makes sense. That's our mask. I was hoping to see it being interacted using bitwise operators, but that's not what we saw. So we basically figured out this function with a little help from the SDK and our knowledge of what TraceLine does. Now our next step is we're either going to hook this or call it to get to work with it. That's going to be the next thing.
I really hope you enjoyed this video. Again, guidedhacking.com/donate, patreon.com/guidedhacking. Please support us so that we can continue to make videos, and peace out.